Alright, hey everyone. Hope you guys are doing well. Happy studying. My name is Mark Lin. This is the heat of reaction worksheet. Disclaimer, I do speak a little bit slower, so please feel free to speed up the video to your liking. And yeah, without further ado, let's get into it. So for number one, it says the decomposition of aluminum oxide is illustrated below. Alright, let me erase all this. This is my second time recording it, because the first time I did, I kind of made a mistake. But okay, you're back at it. So for 1A, it says, is this reaction endothermic or exothermic? So look, right, the enthalpy is on the outside. And since it's on the outside and it's positive, it's requiring it. You need this heat. So because you need to require it, heat is going into the system, it's going to be endothermic. So 1A is going to be endothermic. Alright, for B. For B, what is the enthalpy change for the formation of 1 mole of aluminum oxide from its elements? So, the formation, right? The formation of aluminum oxide. We can't use this equation because this is we're decomposing aluminum oxide. But 2B says for the formation. So we need to flip this so that aluminum oxide is being is formed, right? So this will be 4Al plus 3O2. This will form 2Al2O3. And then since we flipped it, we changed the sign of the enthalpy, so of the heat of reaction, right? This will be negative 3,352. And so it asks for the formation of 1 mole of aluminum oxide. This shows 2 moles. For every 2 moles of aluminum oxide, we have negative 3,352. Right? This is going to be. So this is also a rate, right? So negative 3,352. So that 2 moles of aluminum oxide over 3,352 kilojoules. Alright, this is your rate. For every 2 moles, we get negative 3,352 kilojoules. And so it asks for every 1 mole of aluminum oxide. Alright, we set up a table. We set the 2 moles on the bottom so that units cancel out. Moles cancel out. And then we're left with here, right? 3,352 divided by 2. Right, don't forget this negative. Negative 1,676. So B is going to be negative 1,676 kJ. Okay, and then for C, is this reaction in B endothermic or exothermic? Well, look, this enthalpy change, right? This enthalpy, it's negative and it's outside the equation. So when it's negative, you're releasing it. The system is right here. Let us say the system is right here. Since it is negative, we're losing this heat. So it's releasing. And when the heat releases, that's called exothermic. C is going to be exothermic. Alright, so your answers. Alright. And now on to 2. Boom. Okay, so number 2. Right. So using reactions A and B below, A and B, what is the heat of reaction for the following reaction? So we need to get this, and we have these 2. So we need to manipulate these A and B to get something right here. So the way to approach this problem is look at what's not needed, right? There's no exact way to like step-by-step process to do this type of problems. It's just continuous repetition, and you'll just know it. So look, in this equation, right, there's no O2. We don't have an O2 here. However, in these 2 equations, we have an O2. There's one O2 right here. There's one O2 right here. And this means we need to cancel one of these. We need to cancel these O2s. So which one do we flip? That's the next question. Well, look, A, 2AL. And then the reactant side of the reaction that we want, 2AL is on the reactant side. So this has to stay the same. Reaction A has to stay the same. For B, however, Fe is on the reactant side, Fe is on the product side. So we need to flip this one. So let's flip this one. So it'll be Fe2O3, 2Fe plus 3/2O2. And then since we flip it, we change the heat of reaction and change the sign. Let's get rid of this one. Alright, cool. And so, bada bing, bada boom. The 3/2 cancels out. And we're left with AL, right? AL, 2AL. Put this Fe2O3 down here. Why is it always like? Hopefully that's not annoying. Okay, and then right, bring this 2Fe down here. Fe plus Al2O3. Al2O3. And then, because of that, and then now we just add up the heated reactions, right? This is our final equation, and it matches up with this one up here. So we just add negative 1,676 with 8,000 or 822, and then from that we get the heated reaction is going to be negative 854 kilojoules. Boom. There we go. Alright, on to number 3. Alright guys, buckle in your seatbelts. We're gonna accelerate. So last problem we had 2. This one's gonna have 3. So calculate the heated reaction for 2N2 plus 5O2, which brings us to 2N2O5 with the reactions below. Right. So, what's up here? Okay, so there's 1N2O5 right here out of the whole equation. This is in the product. This is in the reactant side. We need to have this in the product side. So we just rewrite this one. We just flip it, and then look. Right, we need to flip it, and then the product side is 2N2O5, but right now we have 1N2O5. So we need to flip it and multiply by 2. Right? Yeah, plus. So it's going to give us 4HNO3. Right, you multiply by 2, and you flip it. And then this is going to be me, I'll do this wrong. 1 second. Okay, I'm back with the calculator. So we have 4HNO3, right? Because you flip it and then multiply by 2. And it's going to give us 2N2O5. Plus 2H2O, right? The enthalpy change, right? We flipped it, so it's gonna be positive 76.6, and then we multiplied it by 2. So it's gonna get this. Oh, wait, hold on, 76.6 times 2. So this is gonna give us 153.2. Right. So, next step, right? This has an N2 on this side, N2 on that side. There's only one N2 out of this whole equation. And look, this N2 is 1/2, this is 2. So to turn 1/2 into 2, you multiply by 4. So you multiply this whole equation by 4. So this will be 2N2 plus the cross cancel, so this will be 2, so 6O2 plus, same thing happens for this one, 2H2. So we give us 4HNO3. And then the H, it'll just be negative 174.1 times 4. This is gonna give us negative 696.4. Yeah, I don't need to put kilojoules. Okay, and then this one, right? For the first one, we have to look. This one we have to. So this one has to be the equation that we have to flip it, or we have to manipulate this one because look, there's an H2 right here. Oh, hold on, I can just erase. I can erase B and C. Right. So look, right now there's an H2 on the reaction side, and this equation doesn't have an H2. So because of that, we need to cancel out this 2H2. And the only way to do that is by flipping this one and multiplying by 2. So we can get this H2 one that's on the product side. So this will be 2H2O plus, alright, no. And then the sign. And then this will be 2H2 plus, multiplying this by 2 will give us 1O2. And then it's just this negative 285.5 0.8 times 2. Oh wait, no, because since we flipped it, we just changed the sign. So it's gonna be 285 times 2. Which is gonna be 571. 571.6. Right? And then here, I believe we can start canceling things out. So the H2 can cancel out. H2. HNO3. These can cancel out. 4HNO3. And then the H2O. H2O right here. 2H2 right here. And then so we can just combine them together. So we have 2 and 2. Right, just drop this one down. And then look, we have a 6O2 on the reactant side, 1O2 on the product side. Since 6 is greater than 1, we have to multiply, we have to subtract 1 from 6. So 6 minus 1, alright, will give us 5O2 on the reactant side. And then we just drop this 2N2O5 down here. And look, this final equation matches the one that we want. And so we just add up all these values together. 153 plus negative 696.4 plus 571.6. And this will give us 28.4. Here we go. Boom! Alright. Did you see what I did there? I know. Good editing. Okay, so alright, it's getting a little hot in here. Round number 4. Okay. So for calculate the heat of reaction for NO plus O gives us NO2. Alright. And so we have these two equations. So let's cancel out first, right? So look, there's an NO right here, and there's an O. We need this NO, this nitrogen oxygen, I don't know, this NO, this O, to be on the reactant side. So this NO, right? This equation has to stay right here because this NO is on the reactant side, and then so the only other place for where there's a single oxygen is in this one. So we need to flip this and divide by 2, right? So we have O gives us 1/2 O2. And when you flip it, this turns into negative, so it's going to be negative 495 divided by 2. And then you get 247.5. Alright, and then let me erase this. Okay. And then, so, so we have NO and O. And then for NO2, O3 and O3. And then, okay, look. There's an O3 right here on the reactant side. There's a 2O3 on the reactant side here. In the final equation that we want, there's no O3 anywhere. So, since this equation, right, this one right here, can't be flipped at all. You don't want to manipulate this one at all because this NO has to stay here. We have to manipulate this one. And so when we manipulate this one, we have to divide it by 2. And the reason why is so that this O3 can become 1 O3. So divide this by 2 and flip it. So it's going to be 3/2. 3/2 O2 gives us O3. So when you flip it, this negative 427 turns into positive 427. And divide 427 by 2, you get 213.5. Okay, so I think you can start canceling things out. So let me erase this one. Let me check my work. Yeah, 3/2 O3, 213, 247. Oh, I made a mistake. Okay, so for B, I think I wrote this wrong as well. For B, wait, did I do? Oh yeah, I just wrote it wrong. This should be negative 247.5. Okay, cool. Yeah, and then now you just add them all together. Yeah. So negative 199. Cause look, let me cross things out now. So O3 cancels out. O2. O2. This 1 plus 1/2 is 1 and 1/2. So 1 plus 1/2 is 1 and 1/2, which is also known as 3/2. And this 3/2 cancels out with that 3/2. And so you're left with NO plus O gives NO2. And so you just add up all these numbers together. Negative 199 plus negative 247.5 plus 213.5. Then you get negative. H is going to give you negative 233. Boom. Cool transition time. What? Boom. Okay, cool. So, number 5, calculate the heat of reaction for this reaction. So, to calculate heat of reaction, right, it's always going to be, when they give you this table, it's always going to be products minus reactants. So, products, CO2, minus the reactants, right here. And then, so it's going to be products, which is CO2, whatever CO2 is, times the coefficient, which is 1, plus, alright, this is products, reactants, prod, reactant, H2, whatever H2 is, times 4, right, because the coefficient of 4, you always draw on the coefficient, and then for the reactants, it's going to be 2, right, the coefficient of 2 for H2O, plus the coefficient for 1, for CH4, which is 1. So you just plug things in, right? CO2 is negative 393.5. And since it's times 1, you can just drop the 1. 5 plus H2, right? H2, you sure you guys know this. It is on the study guide. H2 is always 1. No, it's always 0. So the enthalpy change for H2, for any diatomic, right, is always 0. So it's going to be 4 times 0, which is just 0, right? Minus reactants, 2 times H2O, which is 2 times negative 241.8 plus 1 times CH4, which is going to give you negative 74.86. Right. This is going to give you negative 393.5 minus let's calculate this out. So 2 times negative 241.8, which is negative 483, plus negative 74.86. It's gonna give you negative 558.46. And then look, so this negative negative, that turns into a positive. So you add negative 393.5 plus 558.46. And you're gonna get 164.96. All right, that's it. Happy studying, guys.